Okay, everybody, welcome. This is Monday, and it is day for operating systems. That's what Mondays are about, operating systems. Hello, we're going to get started. All right, so today's lecture is going to be on Chapter 7, which is deadlocks. And we already talked about processes, we talked about threads, we talked about interprocess communication. So today's topic is on the concept of deadlock and how to deal with it from more of an implementation versus a concept point of view. So this is Chapter 7, if you have the book and are reading along. And so what I'm going to cover today is the problem itself, the system model that goes along with it, some deadlock characterizations, what characterizes the situation, methods for handling deadlocks, and deadlock prevention, avoidance, detection, and recovery if we're going to try and recover from a deadlock situation. Recovery is pretty hard because then you have to slow things down, stop things, start things. Sometimes it's better not to have to even recover from it, but to avoid it, not let it happen to begin with, and then we're in a better situation or scenario. So the entire chapter here describes deadlocks and the prevention set for which prevents a set of concurrent processes from completing their tasks and present a number of different ways and techniques for using it. Yada yada. Okay, let's talk about the deadlock problem. As I mentioned in the last time I talked about deadlock, so we need 2 or more processes to deadlock, which is actually kind of funny because I've done this many years in a row, and I even talk about it many years in a row. I don't think it's going to happen this time, so I probably won't put the question on the final, but you know, it's like it's a multiple choice question. How many processes do you need for a deadlock? You know, 0, 1, 2, 3, you know, and then you know, 0, 1, 2, and then like more or something. Anyway, long story short, everyone picks 0 or 1. And you need 2 or more, otherwise you can't have a deadlock. So I know I said this like twice, I think, already in this class. So I'm not putting that question on the final this time. I just think it was funny. I got a kick out of it when I was reading some of the answers in previous exams. I'm like, where are these people? What do they think? You know, obviously they don't know anything about deadlock. You need 2 or more processes to deadlock. So it's a set. Could be a set of blocked processes, or it could be a single process. Something is holding on to a resource, and something is waiting to acquire another resource that might be held by another set of processes. Or you could have one process that holds on to a resource that just won't let it go. So you have other people, or other processes, I should say, waiting for the resource. So here's an example. System has 2 disk drives. Process 1 and Process 2 each hold 1 disk drive, and each needs the other one. So they actually have something, but they're waiting for the other one. So here's an example of 7 for A and B initialized to 1, and we have wait A, wait B, wait A, wait B, wait A. They're waiting. If they're waiting, they're deadlocked. Doesn't necessarily mean that the process isn't running. It has what's called a busy wait that goes along with that. The busy wait could be a situation in which the process is busy checking to see if it can run, and it's not performing any work. Well, it's not getting closer to the goal of actually completing its work because it might be deadlocked, busy waiting. So that busy waiting comes into play in all of these different scenarios, and we can eliminate the busy wait by implementing semaphores and having the kernel manage the blocked process. In terms of, long story short, we're putting a band-aid on the problem by eliminating the busy wait, but the process still can't run if it's deadlocked. So you can have a process that's deadlocked that is not a busy wait, or one that is busy. But the wait is definitely a necessity to the scenario. So you can be waiting without doing busy work. It can just be held. So if I were to ask you to describe a deadlock situation that happens in the real world, here's one right here. Actually, the traffic is only in one direction. As we see, we can only go one way through a bridge. Each section of the bridge can be viewed as a resource. So we have 1 section, 2 section of the resource. If a deadlock occurs, it can be resolved if one car backs up. That's called preemption. So preempt the resource and then roll back whatever processing was done by the first one, and then let the second one get to the process. So preemption is definitely part of the process running. So if you think about this and combine this with CPU scheduling, you can have the scheduler preempt and then have a context switch between the different processes. Check for resources perhaps, and if the resources aren't available, wait the process. So you're not even going to schedule the process. That's the best of all worlds, because then that way you don't waste time scheduling something to run when it's not supposed to run. Or if you see something can't run, you can implement the aging on your CPU scheduler. So once you see the processes is aged, figure out why is it aging, and it's aging because it's sitting there in the queue for such a long time, and then figure, well, it's deadlocked. Then if that's the case, then tell the user, hey, waiting, which is what happens in Windows. You know, a little screen comes up and says, waiting, waiting. Sometimes those recover, actually. For the most part, you're going to close the process down because the window is pretty hosed at that point, or the application's not running because it's locked for some reason. It's trying to be scheduled, but it can't be scheduled. It has to wait. So the CPU scheduler, in some cases, is coming back with that information, telling the user, hey, we're waiting. So several cars may have have to be backed up if a deadlock occurs. Well, several processes might actually have to be stopped, and then if a deadlock occurs. And then to avoid the deadlock, you might actually cause starvation. So what I'm going to do on the final is probably give you a couple different scenarios. You know, put in starvation with deadlock with waiting, and you know, as a scenario here, you know, true false question. You know, can deadlock avoidance lead to starvation? Yeah, it certainly can. In this particular case, this deadlock avoidance technique of backing up, rolling back, and preempting resources is leading to starvation. So these are not mutually exclusive concepts, they all work together. So your avoidance technique might be causing deadlock, or it might be causing starvation or a busy wait or another scenario. If you're going to use a detection and a correction, or maybe you're just going to use an avoidance technique. So avoidance may also cause that as well. Actually, let me just run through the three scenarios that I had mentioned already, actually, in a previous lecture. We could avoid the concept of deadlock actually ever occurring by implementing a scheduler and implementing the process resources so that we never have a deadlock occur at all. Or we could wait for a deadlock to happen and try to prevent it. And then when it happens, we can correct it. Try to roll back or this is a correction technique here. Or we could just let it happen and hope that it never happens. So most operating systems just let this happen and then hope that it never happens. If you're fast enough, if your scheduler is fast enough and your resources are working fast enough, maybe the user will never create a deadlock, which is the hope. And if you don't ever create a deadlock, just know it's there. But what does that do? It makes the operating system less reliable. We talk about reliability for a moment. Does it give it a lower quality? Could potentially, if it's less reliable, things are going to happen. Are you going to have a deadlock with a heart monitor? Probably not. You're going to have an avoidance technique because you can't let it happen and then prevent. You can't let it happen and then resolve or recover from it because that's a real-time system, and the effects of not resolving it fast enough or having to deal with that type of issue that's innate in the system itself is going to cause problems in itself. It's going to make your product unreliable. So you want a product that doesn't ever deadlock. If you're going to have a real-time kind of processing system like a critical, like a heart monitor or a traffic control monitor or airline control monitor, so one of these, or even network traffic actually, you don't want the network traffic to be deadlocked. The router to deadlock, then you know you're going to end up in a situation where no traffic gets through. So here's the system model where we have resources R1, R2, R3, tons of resources. And then we have CPU cycles that the resources are getting, and then they're all located in memory, so we have memory spaces, and then we have I/O devices that work with it as well. So each process type, R1, has W1 instances, well, where they're going to write, or they're going to read, or they're going to wait in terms of what they're doing. And each process utilizes a resource as follows. You request a resource, use a resource, release a resource. So in this particular case, you're going to have a check-in, check-out, and then a release. So if you request a process to run, then you're not going to get access to it unless it is available. So it's kind of like a pre-check. So there's a pre-check, there's a use of the resource, and then there's a put the resource back, or in that particular scenario. So this is basically the system model in terms of how you're supposed to organize your I/O and how you're supposed to organize your requests for the I/O. So let's take a look at the characterization. So categorize in 4 conditions hold simultaneously. So if all 4 of these exist, we're going to get deadlock. We could get deadlock by a couple of them in different combinations, as I was mentioning before. So we need mutual exclusion. If we don't have mutual exclusion, we're never going to have a deadlock. We might have some corrupted data, and that's actually a highly likely possibility, but we're probably not going to have a deadlock. So in a mutual exclusion, only one process at a time can use a resource. So we need mutual exclusion. We also need a hold and a wait for the most part, because some resource has to be holding it and waiting, and the waiting may be indefinite or it might be for a long period of time. So if 2 resources, if 2 processes go to the same resource, one process is using the resource and the other process needs the resource, is that a deadlock? No. Nope, that's a race condition. 2 processes are going for the same resource. I have a pen and 2 people want to use the pen. I'm using the pen. If I'm using the pen, that's not a deadlock. So the deadlock is the process holding onto the pen thinking, I can't remember what I want to write. I can't remember what I want to write in a hold and wait condition. So they're waiting for something. Maybe they're waiting because they need a piece of paper and the person over there has got the piece of paper and they're not letting it go. That's a deadlock situation. But processes use resources all the time. It's a scheduling situation with a race condition if 2 processes go for the same resource simultaneously. One's using it and the other one wants to use it, then they get queued. So the solution to a race condition is to queue it. So that's why we have queues for the CPU scheduler or for I/O scheduling. But that's not a deadlock. So don't fall for that trap. If the other process is actually using it and it's not waiting, the deadlock is the wait. So you can have traffic all the time, but are you deadlocked? No. You can even be stopped on the freeway, but you have to wait for the other cars in front of you to move, but the cars are moving, you're not deadlocked. If all traffic comes to a complete stop and the cars cannot move, then you're deadlocked. They can't move because there's a car accident and the road's completely blocked off, then you're deadlocked. So just keep in mind, you got to hold and wait. There has to be a hold and there has to be a wait associated with it. So a process holding at least one resource is waiting to acquire the additional resources held by another process. In a deadlock situation, there's no preemption. You can't have preemption exist in a deadlock situation, because then if you want to try to cause the deadlock, otherwise the preemption is going to prevent the deadlock from happening, because that's one of the one of the recovery techniques is to preempt it. So you preempt the process. What does that mean? You stop the process. So no preemption, which means a resource can be released only voluntarily by the resource holding it after the process has completed its task. If the resource is allowed to be held by the process and the process just waits and you can't stop it, then you have deadlock. Did you have a question?
Yeah, there's some confusion between the race condition and the deadlock.
Yeah, a race condition is simply when 2 or more processes are all gunning, they're in a race, they're gunning for the same resource. One of them is going to get there first. The person who gets there first is going to be able to use the resource. Race conditions also lead to starvation, because if you have a fast runner, they're constant. It's kind of like kids in a piñata, or those things. Candy gets rushed all over the floor. The kids that are faster, that's going to pick up most of the candy, they're going to get, and the other people, they're not going to get any candy, because some resources are going to be kept by certain processes because those processes are faster. So in a race condition, you don't have deadlock, because if you had just gotten there fast enough, you could have used it. And the resource is being shared. It's just not being shared evenly. among everybody else. It's a race. It's whoever gets there first is going to be able to use it. And the other ones aren't going to get there fast enough. They're going to come in second or third place. Sorry, you snooze, you lose. You're not going to be able to use this resource. So you're going to be stuck in a starvation. So that's really the race condition. It's not a deadlock. It's actually a separate scenario in itself. And starvation is a separate scenario in itself as well. So hopefully I clarified that for you. Okay, good. So the preemption concept has to exist. There has to be no preemption in that deadlock scenario. You may also have, and this is voluntary, it's the circular weight. Some textbooks actually say that the deadlock is characterized by the circular weight. Without a circular weight, there's no deadlock. However, I disagree with that, and I have to say that it's going to be a Holden weight, and that the circular component of it is sort of optional. So if there exists P0, P1, P2, etc., avoiding processes such that P0 is waiting for a resource that is held by P1, P1 is waiting for a resource that is held by P2. Basically, one process is waiting for another process, waiting for another process, waiting for another process, and it's all connected in a circle, meaning that every one of them is waiting for, it's the dining philosopher's problem. Every one of them is waiting for everybody else that's in the same group. A process is all wanting to use the resource, but then you have what's called a circular weight. You can have a deadlock without a circular weight. That's when you have one process waiting for another or waiting for another. Technically, the circular weight is the true form of the deadlock, but there could be a deadlock in which, you know, you have one process waiting for another process that's out of the circle. As long as you're waiting for something and that waiting is not going to ever end. So the characteristics here, again, going back to the concept, it's an indefinite wait. The wait doesn't end. If the wait ends, it's not a deadlock. It's just a slow-running process. You have a slow, if traffic is slow, but it's not deadlocked when you can actually move. It might take you 3 hours to get someplace where it only takes you 15 minutes, but it's still not deadlocked. So you can come up with resource allocation graphs. If you're the operating system, you're going to figure out, well, how am I going to allocate my resources to prevent deadlock because I want things to run? And if I have deadlock, nothing's going to run on the system. So I'm going to come up, and I'm the operating system, and I'm going to do a resource allocation graph. Great example. It's a set of vertices V and a set of edges E. You build the graph. So you have a, just like CPU scheduling, you know, you have a bunch of processes that show up. Hey, I want to run. And you pick, well, what order did they arrive, and what do you need? And you can kind of configure the scheduler to work with that group. Well, here's an assumption where you've got a bunch of processes all showing up ready to use resources. So what we can do is maybe build a graph to see if we do it in this order, because we need to allocate the resources. If we allocate it in this order, then we run. If we do that order over there, we're not going to run. We're going to have a deadlock. So it's an avoidance technique to remove the possibility of a deadlock happening by changing how you're going to allocate your resources. What does that do? Adds context, well, not context switching, but it adds time. All of these algorithms slow the system down, which is why operating systems don't check for deadlocks, because if they did, the system would run a lot slower than if they were to just, you know, let things run. Because all this is background processing that gets done. It takes up CPU time. You're not getting any scheduled processes to run at all in this particular case. So if we were to graph it out, V is partitioned into two types. We have P, which is the set of processes in the system, and then R is the set of resources in the system. And then we have the request. Remember, we have the request, use, release kind of scenario to set up. So then in terms of the request edge, it's a directed graph between the two. This is an arrow, by the way. It's a little box on the slide here. And then we have an assignment edge. So we have a request. Just because you request something, it doesn't necessarily mean that you get it assigned to you. It means you're going to get probably in a queue. So we put together a graph, and we have a process, and we have a process type with 4 different instances, let's say, and then we have a request for a resource, and then we have a process that's holding on to an instance of a request for a resource, and then we run it if we're going to run it. So there's all the basic scenarios that could occur. Just imagine you have processes coming in, they're making requests. Some of those requests are going to be granted, and then you're going to be allocated the resource, and then you're going to use the resource, and then you're going to go on to your next processing. Here's an example. Here we have resource 1, resource 3, resource 2, resource 4. So 1, 2, 3, 4 resources. And we have 1, 2, 3 processes. And they're allowed to use the resources in different orders. As an example, process 1 leaves resource 2, goes back up to resource 1. And then control gets given to process 2. And then process 2 is going to go back to resource 3. Now process 3 isn't using anything right now. So you're going to go flipping back and forth. This kind of looks like, remember those little pinball machines, and the little metal ball goes around a different resource. Imagine like a pinball machine. You put a graph together, say, how am I going to roll the ball down here to make sure the ball comes in one end and out the other, and it gets correctly allocated. It has to hit all these little locations in order to get the points that it needs. It's like a pinball machine, actually. So it's funny, the other day someone had never heard of a pinball machine. But, younger generation, they don't have those things anymore in the arcades. Well, the older arcades, the old retro arcades have the pinball machines, but it's kind of a thing of the past. Now they play, what's that, Candyland or whatever that, Candy something or other, whatever that game is. Candy Crush or something, yeah. Apparently it's pretty popular. You guys all know about it? Apparently it's pretty popular. All those things have replaced pinball games and the old-fashioned stuff. Pong. No, Pong was a stupid game, though. I don't know. I shouldn't say that. Some people will disagree with me on that. Pong was interesting for the times. So. All right, here's a resource allocation graph with a deadlock. And we have a deadlock because we have, what do we have? We have P3 not going out of the system. He's coming back in here, resource 2. Resource 2 is given to P2 and to P1. And we got P2 waiting for resource 3, but resource 3 is held on by P3. So when it ends up, we have a circular kind of graph going on, then we end up with a deadlock situation because they're not going to release the resource until they get the new resource. They're not going to get the new resource because somebody else is waiting to release their resource before they get a new resource. So the trick to the game is to release the resources. So we have to, attendance is going on now, so let me pause this video. Okay, let's resume back. We were looking at the resource allocation graph with a deadlock. So here's one without a deadlock, and without the deadlock, we see there's an end to it. And we don't have this guy coming back waiting for this guy, waiting for this guy. So as long as we have a break in the graph so that we can end a process and take away its resource allocation and have it use, have it be reallocated to another resource and not wait for another, we have a situation in which we have this particular not so good. So you don't want to see circles in your graphs, long story short, because if it's a circular cycle, if you see a cycle in the graph, you're going to end up with a deadlock situation. So here's a graph with a cycle, but no deadlock, because the cycling is going through back and forth between two resources instead of one. So instead of our cycle coming back, and this guy here seems to be very popular, this guy's very popular, that guy's very popular, we still have a situation in which we can preempt if we need to, and we have P1 going back and forth. So we do have a cycle, but we're not looking at a deadlock situation. So what can the operating system do? The operating system can, when all these processes come into the ready queue, they can go, well, okay, let's put the graph together. If we're going to do this, kind of a long process. If we wanted to do this, it's possible they've experimented with it in the past. In the past, it does work. You could put all together these old graphs and figure out, well, which one's good, and then pick a graph and then run it on that schedule. So you're predetermining when a process is going to run, what order they're going to get the resources, regardless of what would be the fastest per each process. So here's some basic facts. If a graph contains no cycles, then there's no deadlock at all. If a graph does contain a cycle, which means you've got a situation in which you've got two or more going for the same resource, and you've got a cycled pattern appearing in the graph, then if only one instance per the resource type, then you have a deadlock. And if you have several instances per the resource type, possible deadlock, but we don't know. See, here we have multiple instances. What does that mean? Well, if we have one CD-ROM drive and we have to use that single CD-ROM drive, we could possibly have a deadlock. If we have multiple CD-ROM drives, then we just put it to another CD-ROM drive. Put it to another one, put it to another one. What do we get with that? Well, USBs usually have multiple channels, multiple IDE drives, multiple things, depending upon whether or not you actually have just one of that resource. What about CPU? That's also a CPU. That's a resource. CPU could be deadlocked. If something's running and it just can't stop, nothing else on the system is going to run, the entire system is going to go down. You're not going to deadlock your CPU, hopefully. Memory thrashing can cause an entire system to go down too, and I'll talk about memory in another chapter. But so here we have the cycle concept, meaning that if you have the resources, you could throw another one in there into the mix. Then you're going to end up with no deadlock situation. So methods for handling the deadlocks: ensure the system will never enter into a deadlock state. So you do the graphs to make sure that no state's going to occur. There's other techniques as well. That's just a popular way of doing it because graphs are pretty easy to do and they're pretty efficient as a data structure. You could allow the system to enter a deadlock state and then recover from it. So you're doing deadlock detection instead of deadlock prevention or deadlock avoidance. So in the prevention, you're never going to let it happen. In the detection, you're going to let it happen, but you're going to recover from it. That's a little bit more risky because then you can have possible data loss, possible problems with the system. Or you can ignore the problem and pretend that deadlocks never occur in the system. This is used by most of the operating systems, including Unix. So on a final exam, I'll put this down here. Most people who haven't been attending the course, who has no idea about deadlocks, will go, wait a minute, that just seems wrong. Ignore the problem and pretend it doesn't exist. That seems like a wrong answer, actually, on a multiple choice question, but it's always the right answer for deadlock. Happens all the time. Why bother? So let me talk a little bit more about prevention. Restrain the ways the request can be made. Allocate only one CPU for certain things and the other CPU for other things. Make certain process only available to use this drive and then they can use that drive. The order or the resource itself. Create mutual exclusion. So it's not required for shareable resources, but must hold for non-shareable resources. Create a mutual exclusion and then make it so that they can't go in unless they have everything they want or they need. On the hold and wait, you must guarantee that whenever a process requests a resource, it doesn't hold on to another resource. So only one resource at a time. So you use one resource, you let it go. You use another resource, you let that one go. You're not holding on to multiple resources, waiting for another resource. If you are, then the scenario is hopefully not going to exist in the system if you're trying to prevent that thing from happening. So is that you're using buffering. So if you copy a file from one drive to another drive, you're going to open the first drive, copy this stuff into a buffer, close the drive. You're going to be out of there. You're not holding on to that resource anymore. And then you're holding on to resource number 2, which is your second drive, and then you're going to copy it to a file. So you're going to basically release resources as soon as possible. And then the design of that's going to be in the programs that you write, or the system writes. The operating system programs themselves are going to be designed for single resource usage. So it requires a process to request and be allocated all of its resources before it actually begins its execution, or allow the process to request resources only when the process has none and it's able to request a resource. So what does this lead to? Low resource utilization and starvation. If you can only use one resource at a time, then you've got the situation in which you're taking a resource, using it, creating some temporary information from it, and then using another resource. That's slow. You're buffering it in between, but that's really, really slow. So that's what it means by poor resource utilization. You can't use the resources that are available to you. And then that starvation situation as well, because if you need it and you can't get to it because you already have a resource, you're going to be standing here holding this, waiting forever. You're going to, even if you put it back, you're still going to be waiting because you need this one as well. So, also in the preemption, No preemption. So if a process that is holding some resource requests another resource and cannot be immediately allocated, then the resource currently being held needs to be released. You have to prevent it. So in a prevention concept, you're going to put in preemption, and you're going to get rid of the no preemption scenario. And you're going to preempt a resource. Resources are added to the list of resources while for which the process is waiting. You can actually tier out the queues. So you have a special queue for high priority processes that have been preempted. That will hopefully eliminate your starvation. Because if you got to the resource, it's almost like here you went through the line, you got to the top of the line, and you needed to go get something from your car, or you needed to go get a piece of paper from another counter. Are they going to put you in the back of the line? That would be really bad. Then you'd starve over at the DMV or wherever you were because you'd never get to the front of the line again in a reasonable amount of time. So what they do is they give you, oh here, come back to this window when you're ready. So you can do this with processes. You could send a process away. All right, you're not getting this resource right now. You're going to go over there first, and then you're going to come back and you're going to beat the line. You're going to come up to the front of the line, and then you're going to be serviced at this particular counter. So it's a way of queuing it, preempting it, and queuing it in a higher priority so that the process actually finishes, avoid starvation. So a lot of these techniques for prevention, you have to think about avoiding starvation for the most part. Otherwise, you take one problem and then you cause another one with it. So you prevented one problem, yet you caused another. Let's see, the process will restart only when it can regain the old processes as well as the new processes that it's requesting. So it'll restart when it gets ready to, has everything it needs. In terms of the circular wait, you're going to impose a total ordering on all the process types and require that each process request resources in an increasing order or a enumeration. So you're going to put an order on the processes. And you're going to say, to prevent the circular wait, you're not going to get it going back and forth. You're going to get the order implemented, and if the order is there, then you hold on to the order, and you only allow the ordered processes to execute, and then you basically avoid the circular issue. So one's not waiting for the other, is not waiting for the other. It would be impossible. The wait is not going to occur that way. Okay, so let's talk about avoidance. So it requires the system has some additional priority information available to it. So the simplest and most useful model requires that each process declare a maximum number of resources for each type that it may need. So you're putting a limit on the resources and the types of resources that it needs. And in terms of the avoidance, your Deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. So we have a monitor who's out there who's avoiding it. And the avoiding is in the design of the system. So you've got a maximum number, you've got it fixed so that regardless of what order everything runs in, it's not going to happen. You've avoided it from a pure configuration perspective. You're going to avoid it. So resource allocation state is defined by the number of available and allocated resources and then the maximum demand of the processes. Actually, avoidance doesn't necessarily hold true for all operating systems, but it can be used in some situations. As an example, if you're on a microwave oven, you're going to avoid deadlock because you're not going to allow certain things to happen. If you put in something, you're going to have to clear it before you can start again to do something else. So you're avoiding deadlock because you can't have the door opening and the microwave coming on simultaneously. It's not going to work because the operation doesn't work. On a user's computer and a Windows desktop environment, you can't tell the user, no, don't run your Word program until you run your web browser. And don't do that until you run your email program. You can't predict what's going to happen in there, so sometimes the routine of the resource allocation and the number of processes and the configuration for how things are going to run is not determinable. So, but you could put it in the design of the UI, then you could avoid it from a systems perspective, which means you always have to do this, you always have to do that. In fact, transmissions avoid issues as well when you always have to go into neutral. If you haven't noticed, like certain hardware devices avoid issues mechanically by going into a neutral state. And then, so if I'm going to first gear, I can't switch into reverse. And not only that would destroy my transmission, but it's avoiding the situation. It's an avoidance technique by going into neutral first. When you go into neutral, then your system's going to slow down. The parts and pieces are going to slow down enough to where they could actually go into another state, and that would be a safe state or a safe condition. So going on to the concept of safe state, that's what I basically described for you, was transitioning processes in the system so that their next order of execution isn't going to cause harm to the data or to the system itself, or in the case of a transmission, isn't going to knock everything out of place. So when a process requests an available resource, the system must decide if immediate allocation leaves the system in a safe state. So on an operating system, if you're going to do it, you have to decide, well, if you're going to go from first gear to reverse, we're going to go into neutral first so we can determine if it's going to be safe. Then we're not going to allow it. We're going to lock it. Actually, if you haven't noticed that, sometimes you have to actually slow your car down a little bit. Otherwise, you go try to shift it and won't go because your car's going too fast. Or you won't. In fact, newer transmissions do this for people who drive manual transmissions who don't know how to shift properly. If you're trying to go into a gear and the gear is not safe, it won't let you go in. You'll be, I'm trying to shift, but it won't let you. You have to either slow the car down a little bit or get into the right gear first and then go into the next gear. Long story short, that's a safe state determination, and it's determination by that neutral kind of zone. Well, we don't have neutral in an operating system. Instead, we have the CPU scheduler and we have all of the other different systems and algorithms that are running that are going to determine this for us if we're going to put this in. What does that mean? Slower response time. Before we even start the process, we got to figure out, is this going to be safe if we run this process? So I loaded up Word and I loaded up my web browser, and now I'm going to load up my email program. My system's going to ask me or try to figure out if it's safe before I load my email. So then, that particular scenario, as a user, I'm going to be, well, it's not loading. Why is it not loading? So safe state determination slows the responsiveness of the system down. It makes it so that the system, from a user perspective, seems like something's locked, something's not working. And then what if it doesn't want to load? Then you're going to end up with a situation in which, wait a minute now, it's not going to load. This happens on mobile devices all the time. We just try again, try again, try again. It's like when you try to make a call, but you can't make a call, it just fails on you, so you're going to make another call. The user doesn't mind, just keep trying it. Eventually it'll work because a safe state will exist, but maybe the phone's off the hook, or maybe there's a call in progress and you're trying to make another call. So it just won't allow you to do it. So system is in a safe state if there exists a sequence of processes of all of the processes in the system, such that the process that's going to be assigned to the resource that's going to be assigned to each one of the process exists and is satisfied by the current available resources plus the resources held by the process. So if everything is going to work, then we're going to let it happen. The resources are available, processes that want to access those resources are available, then let's go. Let's let it happen. So that is, if process one, the first process resource needs are not immediately available, then the P1 PI can wait until PJ has finished the process and then start it next. So, and then if PJ is just finished, then P1 can obtain the necessary resources. It can execute, return the allocated resource, and then terminate. So it's just like pressing a new call on your phone over and over. As soon as the old call ends, then the new one can start. So it doesn't queue it up though, it waits for you to restart it. So when P1 terminates, P1 plus 1 can obtain the necessary resources and so on. So we can figure out if there's going to be a state safe ahead of time. So the basic facts. If a system is in a safe state, then there's no deadlocks. These little boxes are arrows. Leads to no deadlocks. If a system is in an unsafe state, we could possibly have a deadlock. There's no guarantee. On the avoidance, you ensure that the system will never enter into an unsafe state. Then you have avoided it. So it's not a prevention, it's an avoidance by configuring the system so it doesn't happen. As an example, you can, in a non-operating system example, let's say an example of a checking account, and you're trying to avoid paying overdraft fees. So you can avoid paying overdraft fees by keeping a small buffer in there just in case. That's an avoidance technique. But you can also prevent overdraft fees. If you prevent overdraft fees, you're going to use another technique that's going to make sure your balance never gets to a certain level, because you're going to keep track of all the credits and the debits to make sure that everything is going to balance out correctly. They're both accomplishing the same task, but on the prevention, you're looking more into it. The avoidance is a little bit easier because you're just going to design the system so that only on certain days of the week you spend money. Or this amount, this buffer kind of just stays in the account constantly. It doesn't matter what I do with my checks. As long as this little buffer is in there, I'm going to totally avoid it completely. So it's just kind of like the same sort of solutions in terms of processes for thinking about how you're going to deal with the processes, but they're just different approaches. So it's kind of like the chicken before the egg kind of scenario. Are we avoiding it or preventing it? Well, aren't we doing the same thing? Well, to avoid it basically means you're going to keep your lifestyle the same. You're going to do everything the same. You're just going to avoid it from happening by ensuring that it won't happen. The prevention is we're going to change our lifestyle. We're going to change things as a process so we can't do it. So it's avoidance prevention. So there's a little gray area in between the two. So here we have a safe, unsafe, and deadlock state. So deadlock is going to occur in the unsafe. If we create a majority of our time safe, then we can do the ostrich approach, the head in the sand, and totally forget that there's a possibility, and then when it happens, just let it happen. Don't do anything about it when it happens. Let the user control, delete, reboot the computer. But if this is big enough, if it's safe enough, our unsafe is only going to happen a rare amount of time, hopefully. So the avoidance algorithms, there's a single instance of a resource type, and you use a resource allocation graph perhaps to allocate out the resources. And then we have multiple instances of resource type. We can use a banker's algorithm. The banker's algorithm checks to make sure that you're going to put something back. So we actually went through the banker's algorithm as well. It keeps track of shared resource money. You have multiple people who you're lending money to, and then you have multiple people who's putting the money back in. And you organize the order in which, so all the payments are due at this time of the month and all the loans are issued at this time of the month. So one comes before the other. So you're essentially scheduling out the series of transactions so that everything balances out in the end. So if the transactions occur out of order, that's when the banker's algorithm fails. And then you have deadlock that's going to happen if it happens out of order. So it's kind of like the no money in the account scenario. And the people who want to borrow the money can't borrow the money. Everybody's stopped at that point. People who want to give the money back can't get the money back. So, well, they could, but sometimes the algorithm is going to stop the process. So resource allocation graph schemes. We have a claim edge where process 1 with resource 1 indicates that the process may request the requested resource representing by a dash line. And here's our dash lines, which means they can request the resource. We have process 1 and we have process 2. We have resource 1 and resource 2. Resource 1 has been allocated out. Process 2 is coming back into the resource. And that's the claim edge. How much do you need? What are you returning? So it converts the request edge when a process, it converts to a request edge when the process actually requests the resource. And the request edge is converted to an assignment edge when the resource is actually allocated to the process. So we have this is what the claim is. Here's the request. Here's the allocation. And then we have the return of that, the release. So when the resource is released by the process, the assignment edge turns into the claim edge again. And then, so basically the dotted line is indicating the options that could occur depending upon the situation. And then we judge the situation so that only one of those options can occur at a time. And then we rotate back and forth between the options. It's just a way of avoiding a problem. So, An unsafe state in a resource allocation graph might look like this, in which we have a resource 1 and a resource 2. And then we have this happening. So it's kind of the scenario where we have a circular. If I'm going to, I loaned money to somebody, and somebody's paying me back, and I have another loan out to somebody else, I'm waiting for that money to come back. And so if that money doesn't come back, I'm going to be in trouble as an algorithm. So it's unsafe because I'm going to be in trouble if that money doesn't get returned, and I'm betting that the money is probably going to be late a couple of times. So that's when the government can say, hey, you can charge them fees. Because then you have to use other funds, because the funds that you were waiting to come back into the system doesn't work. It's kind of like when you loan a friend money, you say, well, I'm going to loan you $20 today, and you're going to give me the $20 back on Friday. This is Monday. You're going to give it back to me on Friday. And I'm expecting that $20 to be back on Friday, but the $20 doesn't come back on Friday, then I got a problem. So it's unsafe between Monday and Friday in terms of its determination. Could be safe. You could give me the $20 back on Friday, then I'd be okay. So here's the resource allocation for the graph, resource allocation graph. This is just the unsafe resource allocation. So suppose that process B1 requests a resource. The request can be granted only if converting the request edge to an assignment edge does not result in the formation of a cycle. We don't want a cycle in a banker's algorithm. That's one person waiting for the other person to return the money before they can actually borrow the money, use the money. So it's kind of like if you're waiting for a deposit, then that's a cycle. Actually, that's a month-to-month. So they call it living month-to-month, actually. It's a cycle. If you're putting a cycle in, you could actually come up with deadlock situations with that. Especially if the paycheck doesn't post before the credits post, or the debits post, or whatever. So going back and forth. So banker's algorithm, we have multiple instances. We have multiple borrowers and multiple returners. Each process has maximum claim use. You have a balance, and then you also have a maximum amount that you can borrow. It's got a credit card system, actually. This is the credit card system. When a process requests a resource, it may have to wait for the resource. How many times are they going to tell you on your credit card you have to wait? So it's a modified banker's algorithm with an artificial bank. So when a process gets all of its resources, it must return them into the infinite amount of time. So in a finite amount of time, which means you have to make monthly payments. You have to send stuff back. If you don't send stuff back, the algorithm doesn't work because the money's not available for somebody else to loan. So here's our data structure for the banker's algorithm. In the some previous sections of this course, I had you implement a banker's algorithm. You don't actually have to do it for this class. So none of the assignments are going to have you implement this. But it's not actually pretty straightforward. It's as straightforward as the producer-consumer, I believe. So let n be the number of processes and m the number of resources. We have a calculation for the available, which means how much do we have of the resources available. The maximum, how much are we going to give to each process from each resource. If we allocated everything out, the bank only has 100,000 in it. That's going to be allocated out per process or per user, account holder. How much is that going to be? So that's going to be determined. And usually they determine that by your ability to pay it back, actually, which is how we get loans. And then the need. How much are you want to borrow? This is how much we're going to give you, but how much do you actually need? So which is the other option there. And then the safety algorithm for that is let the work and the finish be vectors in the length m and n respectively. Put it all together in a data structure, run an algorithm on it to figure out the coordination between everybody, and then you set the timeline. So on this date you're going to borrow this, you're going to return this on this date. And then because you're going to return it on this date, somebody else can borrow on that date. We put it all together in the operating system, and then we let the processes run. And then hopefully everybody returns on time and borrows on time, and everything orchestrates together. And we come up with a safer request. And what are we really doing is we're ahead of time determining that we're going to wait for something before we implement something else, before we take it. It's like, so going to a real banker's algorithm, it's kind of like waiting for your paycheck before you spend your paycheck. If you're in that month-to-month cycle and you're working with the resource allocation. So I'm not going to go through the, because we don't have to do it for the assignment, I'm not going to go through the algorithm for this, but this is just one way of actually putting together the graph, and it's basically going to check. And here's an example. Here you have 5 processes, P0 through P4, 3 resource types. You have A, B, and C, and you have the allocation of A, B, and C, the maximums A, B, and C, and the available for A, B, and C, and you're going to basically map out the processes and which ones are going to have access to the resource and which one needs so many resources. Very similar to CPU scheduling, actually. You're scheduling the resources, actually. So instead of, it's the same concept, but you're scheduling ahead of time what order of events are going to occur with these transactions. It's kind of like how we schedule our money. You know, at certain times of the month, you're going to have deposits being put in. And at other times of the month, you're going to write checks. So actually, a lot of people do that. They create their banker's algorithm, and then they tier the payments. So if you have automatic payment set up as an example, which I like to do actually, then you have, well, instead of everything happening on the 30th, let's see, how about something happens on the 27th? Something might happen on the 25th, and then something happens on the 15th. If you tier it out correctly and then tier in your deposits correctly, then you've really created a scheduler for your banking algorithm. And everything's on a payment schedule and a receipt schedule. So what messes things up is when one payment doesn't go out correctly, it fails or gets lost in the mail or something happens with the algorithm. Then you have a problem with it. So I'm not going to go through this one. So in terms of deadlock detection, to detect it, let it happen. When it happens, detect that it has happened. So allow a system to enter into a deadlock state. Detect the algorithm, and then you have a recovery scheme that goes along with it. So if you have a single instance of each resource type, you maintain a wait for graph, and then the nodes are in the processes. The nodes are processes in the graph, and then you keep track of who's waiting. So you can traverse the graph to see who's waiting for resources, which means you've detected, hopefully, a deadlock state. So periodically invoke an algorithm that searches for a cycle in the graph. If there is a cycle, then there is a deadlock. That's time consuming. So what are you going to do? You're going to put a separate algorithm out there to run on the operating system in the background to constantly check for deadlocks. You might as well just put, well, it's kind of like an automatic garbage collector. How often is it going to run? And when it does run, how many resources is it actually going to consume in its running process? And what if there's no deadlock? Then it ran for nothing. So it's like if you're not allocating any processes to something, why are you wasting time checking to see if you've allocated too many? So it basically creates unneeded overhead, which is a problem. So just picking it up and detecting it could be too time consuming to outweigh the cost of just letting it happen. So an algorithm to detect a cycle in the graph requires an order into the 2 operations where n is the number of vertices in the graph. It could be computationally expensive depending upon the number of resources that you have and the number of processes that you're running. So here's the wait for graph and the resource allocation graph. So you take the resource allocation graph, you create a wait for graph, you see who's waiting. If there's a cycle, you have a deadlock. Then what are you going to do? Release all the processes. How do you know which ones are deadlocked? Well, all of them should be deadlocked in the cycle, but then you have to spend more time to determine, well, which one am I going to release? How am I going to free up the deadlock, resolve it, recover from it, which is, again, another time consuming. So in the meantime, the user probably could have just turned their computer off and turned it back on and ended up in a safer state faster for the most part. So several instances, if there's several instances of resource type, you have more graphs, so you have an available piece of information allocation and then a request piece of information that you're going to keep track. And you're going to log these for all processes and all resources. So then you're going to build multiple graphs for multiple different instances of the resource type. Same kind of scenario, but you complex it with several different duplications of the same effort. So the more resources, obviously, and the more instances of the resources, the more graphs you're going to create, the more of an overhead you're going to build into the system for the most part. For the purposes of the final exam, you do not need to know the efficiency of all of these different techniques or the implementation of all these different techniques. All you need to know is the concept of what they are. What does it mean to detect a deadlock? It means to go out there and look for it. Use a technique to detect it. Here's a bad. It requires a high order, whether the system is in a deadlock state or not. It doesn't really matter. The magnitude of a detection algorithm is just too high. It's computationally expensive, which is why it's not done. But, you know, why are you going to detect it? Because you're going to try and recover from it? Which is another thing, too, is like, at one point, why do we care? So going back to what I've said before, most operating systems, they just implement a don't care algorithm and don't do any of this stuff. Because it's like those people that constantly every day check their balance. It's too much. It's computationally expensive, resource-wise, for your brain to actually keep looking at everything every day. So you just want to rely upon a balance being there, so you set the scheme up so you don't have to check it every single day or every single hour, every time you spend something. Which is funny because people do that, actually. They'll check constantly. But it's like, just rely on the algorithm. You know, if you're waiting for your debits, you're waiting for your credits before you do your debits, then everything's just fine. You don't have to know exactly what your balance is at any moment of time. Except for when you get a hacker who comes in and takes compromises your account. Then you might be worried about it. That's when you have fraud protection calling you. So. All right, examples of deadlock. I'm not going to go through the algorithms themselves. We don't need to do that. In terms of the usage, when and how often to invoke depends on how often does a deadlock actually going to occur. If you don't think it's going to occur very much, then don't try. So if you have like 5 or 6 processes running, or 7 processes, then the operating system could switch on the detection. But if you only have 1 process running or 2 processes running, you don't really need to put it on. So earlier implementations of this were dependent upon how much the system was actually being used. And then at high usage, you're just going to make the higher usage run even slower because you're going to put the avoidance on top of it. How many processes will you need to roll back when a deadlock occurs? That's an interesting concept as well, because if you detect it, roll everything back, it's like start all over again. Let it all run it, start it all over again. Let it all run it, start it all over again. Nothing is going to run in that particular scenario. So you're going to start it all over again, or you're just going to pick a couple of them. So for each one of each disjunct in the cycle could be a possible scenario. So if a detection algorithm is invoked arbitrarily, there may be many different cycles in the graph, and so it's not able to tell which one of them might actually be deadlocked or which one caused the deadlock. Because this is assuming you have, in the previous examples, we're concerned with finding one cycle. What if there's more than one cycle? One of them is causing the deadlock, one of them is not. So, or one scenario is leading to it, the other one isn't leading to it, then we got a problem. And then recovery from deadlock is an issue in terms of the process termination. We have corrupted data. What if the process is reading something, it's okay. What if it's writing something? Maybe not so okay. So abort all the deadlock processes. Abort one process at a time until the deadlock cycle is eliminated, perhaps. That's another choice you could do. And then in which order should you choose a process to abort? You're just going to randomly pick a process in the cycle and abort it? It could cause problems in your in your recovery. So you can pick a priority. So if one process keeps getting aborted because it's causing a deadlock, you're going to starve that process. So you can keep track of which one and not pick the same victim over and over again. How long the process has computed might be a factor. How long has it been running? And the new one just came into the system, will then stop the new one. How much longer does it need to complete? Because then that's going to save you time on the rollback. So if you rolled everything back, started them again, well, if one of them is almost done, you can just let that one run. It's going to be faster in restarting it. And what resources the process has used, it may actually be almost done. It has already accessed all of the other resources it needed. It just needed this one more component that it was waiting for. In that particular case, it's better to leave that one alone. Well, how are you going to calculate any of this stuff? You're going to use an algorithm to determine all this stuff. You're going to do that. It's going to take you longer to make a decision. The longer time it takes to make a decision on all this, nothing's happening. The slower your computer's running. So, how many processes will need to be terminated? And if a process is interactive or batch, that may also be a problem as well. So in terms of the recovery from a deadlock with resource preemption, which means you're going to stop a process, you have to select a victim. So we have minimum cost algorithms to determine which victim we're going to select. The victim is this process that's not going to be able to run. We're not going to allow it to run, which is kind of interesting if you can actually do it efficiently. And then your victim, hopefully, is not the same victim over and over again. Then we have a rollback. So we return to some safe state. We put back what we did so that we're going to be consistent, and then we restart the process from that state. So sometimes you may not be able to roll back something that's being written. You have a process that's writing a file to a disk. It's half written. How are you going to roll that back? Undo what you just did. So that causes a problem. And then we have starvation. So the same process keeps getting picked as a victim over and over again. So include the number of rollbacks in the cost factor as well. So what ends up happening is you get a situation in which the process is just never going to run because it can't be loaded into memory. So, all right, well that concludes the Deadlock chapter, chapter 7. Next week we're going to start in with memory. I don't want to start memory today, although we have about 10 minutes. We'll just get out early. I don't want to start memory today because it's convoluted. It's definitely a one-sitting kind of overview to begin with. Memory's not hard, don't get me wrong. It's just it's like CPU scheduling. You can't start CPU scheduling and then finish it over 3 weeks. It's like a one-sitting kind of thing. So next week we will do main memory. I was reminded we're almost halfway through the course. So hopefully you're working on assignments and you're turning them in. And I believe you have everything you need for this course. So you should be able to work. Any questions, comments, or concerns this week? Then we get out now. We're all done for this week. See you next week for main memory, which is chapter 8. If you have the book, I highly recommend reading the chapters, because I'm only giving you a summary of the chapter information in the lectures. And the book is available online.